Hey, what's up, guys? This is Sean here. So this time LeetCode number 1959, minimum total space wasted with K resizing operations. This is an interesting problem. Okay, so you're currently designing a dynamic array, right? And we're given like a zero indexed integer array nums where the element is the number of elements that will be in the array at this time. And in addition, you're also given like integer k, where it's the maximum number of times you can resize the D array. You can resize to any size. Okay, so and the size of the array at time t, right, must be at least this number of elements. Otherwise, it won't be able to fit that many elements, right? And then we have a space wasted. Basically, pretty straightforward. Space wasted is the current size of the array subtract the number of the elements in the array. Okay, and the total space wasted is the total wasted at each of the time. And our task is to find the minimum total space wasted. If you can resize the array at most k times, right? And here note that the array can have any size at the start and does not count towards the number of resizing operations. Right. So for example, we have numbers. We have two numbers here. The first one is 10. Second one is 20. Right. So which means at time 0 we have 10 elements, and at time 1 we have 20 elements. And for this one, we cannot resize the array at all. Right. But obviously, like I said, since to start the array, we can start array with any size. Right. So which means that for this one, we have to start with 20, right? Because if we start with 10, right, then at time 0 is fine, but when it reaches the time 1, we cannot resize the array, right? So that's why for example 1 here, we have to start the array with 20, right? And then the answer will be 10 because at time 0 we have 10, at time 1 we have at time 0, right, we have wasted space 10, and at time 1 we have a wasted space 0, right? I mean, obviously we can start with any size which is greater than 20, right? But since we're getting the minimum total space wasted, right, that's why I will use the smallest. Okay. And then in example 2 here, right, so for this one we can resize it once. So I think the strategy is like this. So we can start with 20. Okay, we start with 20. That's why we have 10 at time 0, right? And then we have 0 at time 1, and when it comes to time 2, right, we have to resize it, right? So which means from resize from 20 to 30, we also have like wasted 0. That's why the total is 10, right? And here another example, right? I'm not going to go through it. And the constraints like this, right? We have 200, right? And the number range is 10 to the power of 6. So for this one, at the beginning, when I look at this minimum keyword here, so basically I'll try to solve. I'll try a binary search first, right? But for this one, I think binary search will not work because let's say binary search, we search the answer directly. If we search the given like wasted time, wasted space, right? There's no way we can figure out given this fixed space wasted if we can make resize this array within the k times, right? So that's why binary search will not work in this case. And then I was also try the greedy, right? So because this one's I think it's most like it will likely be a greedy problem, but basically when I say greedy, I mean probably I can sort the numbers, right, from the biggest to the smallest. But then we have this k here, right? So which means that at each point, right, at each index, I don't think there's like optimal solution here, because at each of the index here, we can resize it to any numbers, right? To any size. I don't think there's like a optimal one, because we don't know what's after this I here, right? We don't know what's after this I, so that's why I don't think I was able to find like a greedy approach. Then it leaves us no option but to try all the possible scenarios, right? So, and then if we were trying all the possible scenarios, and then obviously we should consider DP, right? Because DP, given the DP state, we can avoid processing the similar scenarios, right? So how can we use DP? Yeah, so the answer is yes. And the problem is that how can we define the state, right? So obviously the first state will be what? Will be the index I, right? So which means that we're at the current index I here. And second one is that what? Probably is the k, right? K means that how many operations, resize operations we have left, right? And this is the what? This is basically the maximum, sorry, the minimum wasted space, right? Given this state, basically this means from I to n minus 1, right? So that's the definition of DP. I was thinking about this approach, but then I was like, probably we also need like a third state, which is the current size, right? So I was trying to add this one to the state of DP, because I was like, based on the current size, it depending on if we want to resize the current one or not. Like if we resize the current one, do we have to consider the current size, right? Because obviously it's not that we only resize when the current size is smaller than the number. We might also resize even though the current size is greater than the current number, because we want to minimize the wasted time, right? Let's say we have we have 10, 30, and 20, right? Let's say for this one the k is what? K is 3, because in the optimal way, right? In the uh, best case scenario, we can always resize. Basically here we resize the first one is fine, right? Basically we put it 10 here, the first one doesn't need to resize, and then for the second one we resize to 30. For 20, right? I mean, if we have remaining operations, of course we want to resize it to 20 so that we can minimize the total wasted space, which in this case will be 0, right? So which means that we don't, so resize actually it will not directly relate to this current size, because as long as we have enough operations, we can always resize, right? So and then the next question is that how can we write the state transition function, right? So let's say given the dp I and k here, how can we move to the next state? Right, so we have some numbers here, right? And we're at like current I, we're at I here, right? So how can we retry? How can we move from the current state to the next one, right? So if you want to resize, okay, if you want to resize at this current place, of course, we're assuming that we have enough k, right? So what the question is that which number we're going to resize to, right? So let's say we have 10, 25, 5, maybe 35, right? Something like this, right? No, it could be a 100 here, right? It doesn't really matter. Okay, so we have 100 here, but we don't care about the previous state, right? So if we only look at the numbers starting from I here, okay, so basically we have different numbers here. We can resize it to 10, to 25, to 5, to 35, right? But the problem is that can we use any of the number? The answer is no, right? Because obviously from here onward, we can only resize it to what? To the numbers who is greater than 10, right? And then it doesn't make sense to resize it to 100, right? Because 100 is too big, and since we're trying to minimize the wasted time, right? And obviously this 5 we cannot, even we have a 5 number here, we cannot resize to 5. So which means let's say we resize to 10, right? So we resize to 10, it means that this resize will can only cover this one number, right? Because if we resize to 10 at the current place, it means that when we reach 25, right, we have to resize it again. Otherwise, it cannot move forward, right? But so the next one is 25, right? So what does resize to 25 means? It means that if we resize to 25, it can cover up to where? Up to 5, actually, to either 25 or to 5, right? And then similarly for if we resize to 35, right? It doesn't really, let's say we have a 40 here, right? So if we resize to 35, and then it means that we can cover from 10 to 35, right? So, and then we have I think we have a state transition function here. Basically, from here, so dp of I and k means what? So it's going to be minimum, right, of the what? Basically the dp. So first we have the next state. The next state will be dp k, sorry, j to k. J to k plus the wasted, right? The wasted space. And the j is what? J is between the I plus 1 to n, right? So which means that from I here, we'll loop through each number from the current I to the end, right? And then we'll try to, because and we'll basically maintaining the maximum number so far, because that's going to be the number we need to resize, because otherwise we cannot cover the entire range, right? And here along the way, and then we can easily, if we maintain like the maximum number along the way, I think we can use have O1 time to calculate the wasted space, total wasted space, right? And then after this one, we're gonna pass this one, so it's gonna be k minus 1, right? To j and then k minus 1, which means that let's say the j is here, right? It means that this it means that we're going to resize to 35, which means we'll cover after resizing to 35, we can cover from 10 from this from 10 to this 35, and the total wasted space by resizing it will be what? Will be 35 times 4 minus this running sum, right? And then and then the next state will be what? Will be the j to k minus j and k minus 1, right? Actually, you know what? So here, even though we're trying all the possible ways, but there is like a greedy approach here. Basically, not approach, a greedy idea here. Basically, we only resize it to the maximum number, right? Because that'll be enough. Because basically, we resize to 35, but not 38, right? Because 35 is the smallest that can cover the the numbers from I to the current j. And I think that's it, right? So I think that's the state transition function. And then we can start coding. So dp of index, let's do I and k, right? LRU cache none. So we have some basic case, right? So when I is equal to n, right? We need to return 0, right? It means that we have reached the end. And then the answer equals to system dot max size, right? That's the maximum. And then we need two things. The first one is the max, the current max number, right? And then we have a running sum of 0 that help us to calculate the total space, right? And then we have for j in range of the I to n, right? So we have the max going to be the max of the dot numbers of j, right? So this one is max. Maybe we should use like a new size. How about the new size? I think new size is better. It's more intuitive here. And then the running sum here with the of j. So the answer will be what? The answer will be the minimum of answer plus we have the new size, right? So the new size will cover from j to the current I plus 1. That's the total number it will cover, right? And then minus the running sum, right? And then we do a dp of j plus 1 and k minus 1, right? And then in the end we return the answer, right? So this is what like I said. So first we maintain like the current new size with a max number so far, because we only choose this max number so far, and that's when we can cover the numbers, right? The numbers from I to j. And after that, this is basically this part is like the total wasted, right? For choosing new size as a new operation and covering this this number of elements, right? And then the remaining will be what will be this j plus 1 and k minus 1, right? Um, Actually, there's like another case. Maybe check here, because we should only do this whenever the k is greater than 0, right? If the k is smaller than 0, then we cannot do this. So a trick is that instead of checking k if it's greater than 0, we can move that check into here. If the k is equal to -1, then we can return the system max size, right? This will simplify the code a lot, because whenever we have a case that k is -1, right, and then basically we'll return the system max size, which will basically equivalent to ignoring that scenario, right? And then we have n equals to length of numbers, and then we just return the dp 0 and k, right? Oh, well, one more thing. So how about this one, right? How about this the 0 index one? So at index 0, we don't need to count this operations, right? So how do we have we already considered that this scenario, right? So we have, because let's say for example this one, right? For example, this is the good example. We have 10, 20, right? So at turn 20, right? So we are at index 0, and the case also equals to 0. So for here, we're gonna do two for loop here. We're gonna do two for loop, not two for loop, two traverse, two loop. The first one is 0. The second one is 1, right? So when we do the first loop here, right, we have 0 here, and then the next state will be what? The next state will be dp1 and then -1, right? So this is the next dp state. So obviously so n is equal to 2, right? So since I is not equal to n, and then but k is equal to -1, that's why this one will lead to this invalid scenario. So how about the second one? So the second one is like we'll cover from like what? We'll use 20, right? So the 21 is what? So the 20 after using 20, so the next state will be dp of 2, right? 2 and a -1. But at this moment, right? So what do we have? The I is equal to 2, so which means it will return 0, even though the k is -1, right? But since we check if I is equal to n first, then that's why we can cover this 0 size case, 0 index case. Yeah, so basically we always allow to move forward, but we check if this case equal to -1 after this first if check fails. That's how we handle this. The first index doesn't require like operation, right? And yeah, so let's run the code. Accept it. Yeah, so it passed, right? Because the time complexity for this one, we have I and k, right? So the I and k is, so let's say this is n, right? So the state for this one, the total state number of state is n squared, right? And then for each of the state here, we have what? We have another for loop here, which is like, right, like what? N cube, right? Which is this one. So that's why it can pass with this number length. Yeah, I think that's it, right? I mean, this one is a DP, but the state transition function is a little bit tricky because to be able to find to move from current state to the next one, we need to maintain two variables. So the first one is the new size, right? But basically which size we can pick. And after picking this new size, it means that we can cover the new size, the maximum number so far, right? And after picking this new size, it means that we can cover from this I to this J, all the numbers from this I to J. And with that, we can calculate the time, the space wasted, and then we can easily transit to the next state. Cool. I think that's it for this problem. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye-bye.